that was my Skittle Launcher doing its thing. So it uses OpenCV, a Python library, to detect people, and based on that data it knows where to launch the Skittles at people. So that mechanism has a rotating arm that is a centrifugal launcher, and there's a servo on that which controls whether or not the candy is launched. When that opens, the candy is launched at the person. This is all controlled using a Raspberry Pi. Before I talk about the specifics of this design, I want to talk a little bit about how it works. So in the center, we got the DC motor with spinning. So that arm has a centripetal acceleration. So when we stop the arm and eject the Skittle has a tangential velocity relative to the orbit of the arm. So that allows us to know where the Skittle is gonna go, and that's determined by the program. So here is the base over here where the motor goes. There's a hole over here for the motor to go. Some mounting over here, and here the wires can come out. And onto the motor, we have the arm. So the arm, here we have the motor, it goes onto the motor end, and here we have the servo mount. And on the servo horn, we attach the holder for the Skittle, so it can go this way, it ejects the Skittle out. So the problem with that is that we have a servo. So then the servo is gonna have wires, and the wires are not going to be okay to tangle around since it's going to be rotating. So we need to use a slip ring to deal with that. So I designed a slip ring holder over here, what attaches conveniently to the base over here. So this one is not drilled out, but over here there's going to be a slip ring, and that allows the wires to rotate on the bottom, but they're going to be straight when they come out on the top. So that allows the system to work really nicely and not have any messes. The electrical part about this is probably the easiest part. We only got a few components over here. We got the Raspberry Pi. This is connected to power. Next, we got the L298 and H bridge over here. So here we have power goes in here. We got inputs here, and we got outputs here. The outputs connect to the motor, inputs go to pins, and power goes to the 12-volt wall adapter. The inputs are enable, A, and B. Enable is the pin that provides PWM, so that tells how fast the motor is going to go. A and B control the direction. So it's the motor over here, but then we have 4 more other wires here. So those are the encoder wires. So encoder is 5 volts, so we connect that directly to the Raspberry Pi. And we also have 2 pins over what are input pins, so they take the readings from the quadrature encoder on it. So next, here's a servo motor. This goes through the slip ring, and from there it is connected to power or ground and to an input pin. And we also got here the camera. This just goes directly to the camera port. The programming was by far the most annoying part about this project, but also it was really nice to see it work when it finally worked. Well, for the most part. We don't talk about when it doesn't, but yeah. Let's take a look at the code. Skittle Launcher. So first, we're gonna have a couple of import statements. We're gonna import the Raspberry Pi GPIO pin library so we can interface with the pins. GPIO 0 to simplify some of these stuff. It does it in the background, so we can just do some encoder stuff by just declaring it, and we can easily get the ticks. Then time for some clock function to determine where we are in the time space, and some stuff with acceleration later on. We have numpy for the arrays for the camera, pi camera to gather the data from the camera, and CV2 to have this computer vision. So that will do all the image processing with the hog detector, what we get into later. So first, we're gonna set the warnings to be false because GPIO pin stuff, we get a lot of warnings and they're really not necessary and they just get in the way. Next, Broadcom numbering, because that's usually really easy to use compared to the actual pin numbers. Then the motor pins are going to be initialized here. So we're going to have the enable in 1 and in 2 are going to be controlling the DC motor. Servo is for the servo motor. That's going to be 12 for the servo. And motor initializing the pin. So we're going to be setting up these pins as output pins. And then we're going to start the pulse width modulation on the DC motor, but we're not going to start it yet. That's why we have the low over here. We don't want the spinning before we find the person. It gets really annoying when it starts doing that. Next, we're going to start the servo. So we're going to keep it to a closed position. We didn't have the function right here. It's not defined yet, but we're just setting it to 12, and that is the closed position. Servos, the pulse width modulation is the number of degrees it's rotated, but it's not exactly the degrees. It is something with control of the degrees. Then we're going to initialize the motor encoder. So this is what I was talking about, GPIO 0. It's a really simple way. Like, otherwise we'd have to set up like a lot of interrupts, like to do if it's A is greater than B greater than A, that type of stuff to see like where we are with the ticks. So this thing we can just keep like asking like where we are. So next we have the camera, we're creating that. Then we declare like the frame size, frame rate, how many degrees. So this is going to be used later when we have to find the release angle. So you'll see that. Camera width, it's for us to use. It's easier than going to camera the resolution and getting it from there. Then raw capture is the pi camera object. So then we're going to load up the hog detection. So this is the source for human faces, and it is really good at detecting faces. On a Raspberry Pi, it does get kind of slow, but like on a Mac or something, like it is really good, and it's pretty accurate. And we're gonna store the coordinates of people in the bounding boxes in this boxes array. Then here we have some stuff with the DC motor. So pulse per revolution, that's for the encoder, so we can determine the revolutions. Acceleration time is for us to not start the opening of the servo too early. Loop time is just a little bit of a wait time we got every iteration of the loop. The current angle is going to be 0 right now. That's why like every time I start this, I have to home the arm to 0 because it does not know where it is before. Then we have time previous, time current, and time start. These are all used to determine if it's enough time has passed for the acceleration. You'll see that later. Then the release angle is also going to be 0 for now, but that's going to be changing. But if like say this function does not work, like, or we just like don't use it, it is like it just throws it like straight ahead, so that's pretty fine. Like, so in this camera capture function, we have the release angle global here because we're going to be changing that up here. So it continuously takes some frames from the camera, and this image shows an array of that. Just ignore this gray thing, that's just for some other hard facial detection. Then the hog outputs the boxes and the weights, and we're gonna draw boxes for each of these things what the CV2 outputs for us from the hog detector. So we're gonna draw the box and we're gonna show it on CV2. We're gonna draw a green rectangle, and if we actually get any bounding boxes, we're gonna print them out like the x coordinates. Otherwise we just continue with the loop. Then once we get that, we're gonna keep this x point, and we're gonna, because it's easier than like doing boxes all like every single time here. So release angle is gonna be calculated here. It is really just a translation of like backwards 90 degrees, so we can tangentially get the velocity to hit the person. Then we have a release angle. If it's less than 0, we have to make it positive, so we're adding 360 to it, and we print it out. These 4 over here, open, close, start DC, stop DC, just simple functions to start and stop these motors. And when we start, we're going to close the servo because we want the candy to be in. When we start capturing, we take the initial time right now, so this is going to be used here when we have to see whether enough time has passed that we can leave this over here. Then we're gonna have the not shot, so this will, once this is false, this will stop, and we're gonna start the motor. So in this while not shot, what we have here is we keep taking the current time, so like that will affect in this loop because we have this second thing here that it has to be enough time that has passed so the motor actually accelerated a bit. And here we calculate the current angle based on the encoder steps, really simple, and like using the interrupts like I said before. We print the current angle, so if we should open it, we do open the servo, stop the DC motor, and we this exits out of the loop. Then we set the time to the previous to the current, but this is only if like this doesn't happen. Well, actually, this does happen, but this does not really matter. But next, we have the just in case if the motor does not stop, we just set it off over here, and we put a timed sleep until it stops. My website for this project has some of this stuff explained in greater detail. Let's take a look at one of the pages in the website. So here's the code for that. So I'm going to create a title, do some meta char set here with the character set. We're going to link some style sheets. The main thing is Bootstrap. So we're going to have responsive design done by Bootstrap, and we're using some of its style classes. So there's not too much in my style.css. Then we have a navbar here, first thing. It's collapsible, so when it is on a mobile screen, it will be in a hamburger style. And then we're gonna have the heading for this page, the prototyping, and then we're gonna have headings for all the stuff. So we have a preliminary draft. Here we'll have a version 0, version 0.1, and then below there's gonna be a version 1, maybe a version 2 by the time this gets uploaded. And each of these has a container with rows in them. It's like a table format. So we're using the Bootstrap over here we're setting the column width here down by SM. It's like relative to the window width. And if it is too small, it will be done in the hamburger style again. That's pretty much it to the website.